All right, so a couple things today. We're moving on to new stuff, stacks, queues, and I've been told this is pronounced DEX, not DQ, which is confusing to me too, but that's okay, from Chapter 6. Some housekeeping items. I was behind on posting the quizzes, my apologies. So I posted the 4 and 5 quizzes, but I put them due a week from Thursday. They're pretty short. These are, again, just to get you to open your textbook. If the only thing you do is listen to me, you're not getting enough. Like, there's more there. That's why we have a textbook. That's our main reference here. You don't have to read every single word of it, but like get into it and make sure we're getting the ideas covered. So that's sort of the idea there. And then at the end of this week, I'll post the Chapter 6 quiz. I can even post it early now, I guess. I can just go do that. I just got to change this date real quick. Should I do that, though I don't forget it? Is that 3 quizzes due in a week and a couple days? They're short. They're short. Don't worry about it. And then the next project. Should we talk about the project first? Project 1? Yeah? Yeah. Okay, cool. So we'll talk about the project first. So this is backtracking recursion using playing a checkers game for us. So checkers is a fun game here. My grandpa was really good at checkers, and I was not, but I prefer chess. So we're going to have some sort of 2D list for a board. I'm sure you're bored of bored of boards. That was unintended, but I like that. By now, we're going to assume all the pieces are kings on the board because that makes life easier. If a piece is not a king, it can only move forward, not backwards, and that's probably more checkers logic than we actually care about. We're just using checkers because it helps us illustrate here's something we can do with backtracking recursion, not because we really actually want to be able to play checkers, right? So we're going to have black pieces and white pieces and then spaces. So that'll be our board. Our init method should accept a board and ensure that it's a valid checkerboard or raise an exception. So things that make a valid checkerboard valid, being 8 by 8, and all of the checkers pieces are on the same colored square. Now, I'm okay with them being on the white squares or the black squares, or whatever you want to call them here. Like, so if we look up a checkers board, there might be a valid versus invalid thing, but I'm pretty sure you can use either color. It'll work out to be exactly the same here. So as long as they're all on dark squares or all on light squares, you'll have the same number of checkers on each one, okay? That will make it valid. So that's our valid check. No, 5% off, ooh, that is really pretty, but $140. It's too much for checkers board.
You like checkers?
I prefer chess. No, my grandfather really liked checkers. And I could never beat him, but I gave up after I was done being a kid. It just wasn't fun. So our init method accepts the board, make sure it's valid, and then we're going to have a function called get max jumps that returns the max number of jumps any white checker can go. So to do that, for every white piece, we have to calculate the maximum number of jumps it can go and return that value, the max value of that. So if we look at some checkerboards, checkers positions, I'm sure we can find some here, right? Sure. There are no jumps any of the white checkers can make right now. There's no pieces they can jump over. There's moves they can make, but there's no number of jumps. So one of the rules in checkers is if you can jump, you have to jump, which is an obnoxious rule. So finding out if there's any jumps is useful. So if your max jumps is not 0, then I would know, hey, I have to make a jump somewhere. I'm not just free to move one of my pieces. But the black checkers have a jump. So this piece here could jump and have 2 jumps. Would be its max number of jumps, right? It jumps over a white checker, takes it off the board, jumps over a white checker, takes it off the board. So a couple different options here with our checkers pieces.
Like in these, in case of a board like that, how do you check for the diagonals?
So because we're rows and columns, right? Your diagonals are going to be up a row minus a column, right? Or no, that's direction for you, right? Or up a row plus a column, or down a row, right? Plus a column, or down a row minus a column.
So like from the position we had, row -1, column -1, row -1, column -1, and check for that?
Yeah, that's one of the ways to do it, right? Because to jump over a piece, you need to have an opponent's piece there. You can't jump over your own pieces. So you have to make sure that an opponent's piece is there, and then where you're going to land is empty. So like the white piece could jump over this piece if this piece wasn't here. But because this piece is here, that space is not empty, I can't jump there.
The thing we're going to check for is if the one column -1, row -1 is the like, if you're playing with the black ones, the column -1, row -1 gotta be a white one, and if the column -2, row -2 is empty.
Mm-hmm.
All right.
For that direction, but then for the other directions, right? Because there's 4 directions you have to check.
Right.
Yeah, so we got to check all 4 directions.
So we jump it and then we move the weapon.
Yep, remove the piece. Yep, so we have to do all the steps to modify the board, right? Because you want to make sure that eventually, right? And so part of this exercise is coming up with test cases to make sure that we don't screw this up. I have an 8x8 here. Okay, shrink this down a little. Oh, I can't shrink them all. That's fine. This is close enough, right? So if I had,
What
say,
if you move the white thing? The white one.
thank you. Yeah, okay, that's a little bit nicer. So if I had a white checker here, and a black 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 checker here, right? I could jump to the center here, and then I have 3 other places I could jump. But remember, we need to make sure we modify the board like we did with the maze solving, so you don't jump and jump and jump and jump and jump and jump and jump back and forth like forever. Once you jump a checker, it has to come off the board. So other interesting setups you might have, right? You might have other places you could jump pieces. So if we change this setup a little bit here, let me move it back. If I was here, and then a black checker, and a black checker, and then a black checker, and a black checker, and a black checker. Let's see, is that one of these paths will get me where I want to go? Black checker. Yep. So you get to a lot of interesting scenarios when you have something like this. Like, which path are we going to take to go certain ways or to maximize our number of jumps? Right? If you go to the diagonal, and then the diagonal, and the diagonal, that's not the max number of jumps. That's one possible path, but it's not going to be the most number of jumps we can make. Right? So if we jump to here, remove these, and then maybe we jump to here, remove those, jump to here, remove these, jump to here, remove those, jump to here, jump to here, jump to here, oh, there, right? We can eventually get back to and make this whole circuit here, right? When we jump to here, and then jump over the last piece. So it's possible to get all of the checkers off the board in one sequence, depending on how you're doing it here, right? So the order in which we go definitely matters.
How do we check for that?
You just keep trying. Like, this is what the backtracking recursion is for. Right? So we try a path, and then when we get to the end, we just undo the step and try the next one. So once we've tried jumping down this way, we try jumping the other way. And we try jumping the other way, we try jumping the other way. Like with the maze solver, we tried up, down, left, right. You're just going to try each of the steps here.
So we'll keep trying. So in this case here, if it goes down, you can either go down one again or up and do the whole circuit.
Yep. Well, I mean,
checking for that user recursion.
You have to try all the 4 steps. You have to try all your 4 jumps, just like we tried up, down, left, and right. You try them, and then you start going down that path, and then when you come back, you have to undo that step to make sure you put the board back. Yep. Yeah, so it's fun. There's lots of different ways to go about it. And depending on which way you go first, it impacts it a lot. So that's all. Yeah, and there's other like circuits you can set up and things, and some paths will be longer than others, and but that's sort of the idea. So,
but it should be playable, right?
Well, the boards don't have to be. I mean, they can be valid boards, but there could be no moves. So you say, hey, my max number of jumps is 0. There are no jumps for me to make. That's possible too.
I mean, the player should be able to interact with the board, right?
No. No, we're just calculating. So if we're building the checkers engine to play, right? One of the things the checkers game has to know is if there's jumps, because if there's jumps, you have to jump.
Right.
And we want to find out what the max number of jumps is, and we can probably assume max is, more jumps is better. It's not always the case, but we'll assume, for our basic, let's play like a 7-year-old plays, I want the max number of jumps every time I jump.
So for our class, for our function, one of the arguments, parameters would be a board, is that it?
So the init method has to take the board. So when you create a checkers solver or something, you give it the board, checkers max jump finder, I don't know whatever you want to call it.
Find the path.
Yep, it'll find the max number of jumps. So just calculating number of jumps for one white checker, you get 5 points. Finding the max for all of the white checkers, you get 5 more points. And then the init that takes the board and validates it is 5 points there. So this one's 15 points total. So it's worth a little more than the last project. Not a whole lot more, right? I think the other one was 12. Did I add that up right? How many points was that one? Yeah, this one was 10. Yeah, so this one was 10 points, now we get 15 points. The next one will be worth a couple more points than that. And we'll keep working our way up. That make sense?
What mean from all white checkers? So I have like one piece, Can I explain the criteria again, please? Like the second and third ones?
To be a valid board or for finding jumps?
It says get the max jumps, can calculate max
Yeah.
jumps for one white checker correctly.
Yeah, so like your max jumps will at least figure out how many jumps this one checker can make.
Right, the other one is for every single checker.
Yeah, and then if you check it for all the white checkers, then you get the 5 more points.
Right.
Yep. Yeah, and this one's this is just the loop, right? It has to track the max number of jumps for each checker and find out which was the highest number and return that. So there's a few things here. But yeah. All right, awesome. So let me fire up PyCharm here. We are in, is this week 5 already now? Wow. 5 means we're a third of the way through after this, right? There's only 15 weeks. Well, 1 week is midterm, so really it's 14. And project work time really means there's 13 weeks. So we're more than a third of the way through now. And it's not even March or April. But we got spring to look forward to. All right, so week 5, let me start new project. Call this.
Do you think the book is good for recursion? Do you think it's explained wrong?
The textbook is hard to read. I don't enjoy it. It's a little dry. It's good. It's just a little dry, is all. So this is stacks and queues. So stacks and queues are special data structures. They're special in that we're limiting the things you can do when you hold a bunch of data together for specific reasons. So, and if the problem we're solving fits one of those specific reasons, it's a great data structure. So that's fine. If it doesn't fit, then it's okay. We don't have to use it. So you guys are pretty familiar with stacks, right? Let me just delete this here. Oh, this one here. Let me grab that one. Really? Cut. Okay. I don't know why delete wouldn't work, but I can cut it out, sure. So when you think of a stack of items, right? Maybe we make like a stack of books. What's the first book that comes to your head?
Harry Potter.
Harry Potter? Which one?
I don't know. Sorcerer's Stone.
All right, number 1. Easy. Interestingly, it's called the Philosopher's Stone in England. I don't know why they changed it for the non-English version here. But I have a copy of the English version for long reasons, but it was fun. All right, so that's the first book. We put a book on top of this one. What book goes on top of this one? We're making a stack of books.
Percy Jackson.
Percy Jackson? Which one? Is that the whole series?
No. I didn't read it. I just
Okay.
read this.
All right, so that one goes on top, right? Can we grab Harry Potter right now without moving the Percy Jackson book?
Percy Jackson is a series.
All right, we'll say 1. All right. And is it the lightning? I forget what it is.
Yeah.
Yeah. We'll say number 1. That's fine. So can we get this book out of the stack without touching this one?
No.
No. So a stack is a first in, last out. The first thing that goes in the stack is the last thing to come out of the stack. Or last in, first out. Right? The last thing that goes in is the first thing out. So we're only ever grabbing the thing that's on top. Right? So as we add more books, we have more things on top. Oh man, what was it? The Pawn of Prophecy. That was the first of a series of 5 or 10. I think it was 2 different 5-book series. That was a fun one. The Bellegarde or something? This was a long time ago. So, first in, last out. The ways that you interact with the stack is you push something on the stack, you pop something off the stack, or you peek at the top. Right? Take the top thing and push, you add to the top. Right? So we're limiting what you can do with a bunch of items here because it is useful for how we're interacting with it. Now, if you remember back to, let's open up our other project here. Where's my recent list? There we go. Let's do a recursion here. When we did our maze solver, how about the maze solver? Right, let's do if we found a solution. We'll go in here. And then we'll give this a run. Oh, run in debug mode, sorry. Remember, one of these cool things we looked at when we debug is we see every single function call on the call stack. This is a stack here that's managed by Python. So then when a function gets called, it gets added to the stack. You don't touch the functions below, you only work with the function that's on the top. And when we're done with it, it comes off the stack, and we see, oh, what's next? Where do we leave off here?
Like less in or so.
Yep. Yep, so code itself works with a stack structure. And it makes sense, this is how it flows. Lots of things work well with the stack. When we looked at how we solve the Tower of Hanoi solution, if you don't use recursion, you have to use your own stack. You have to say, okay, here's what we're going to do. Come back to this after we do this step. Come back to this after we do this step. Come back to this after we do this step. You can build your own stack to solve recursive problems without recursion. It's just a big pain in the butt. It's more efficient that way because you don't need to keep all of these function calls around here. But it's a big pain, right? It gets more complex for us to do. So recursion gives us that stack without us having to manage our own stack, which is super cool. So that's a common stack structure that we see. Other fun things with stacks are, depending on what we're working with, right? If we're modeling something that has sort of the stack behavior. So one of the projects we'll work on, we'll work on stacking up a bunch of things for fun and then working them off that stack. The idea, we visualize it as like we're taking containers off of a container ship and putting them on a stack for my high-low to carry or something like that, because high-lows carry those or something. I don't do any shipping stuff, but we'll pretend it makes sense. So as you take a container off, you have to put it on a stack of containers, right? We stack containers 5 high or however high OSHA lets us do that, because more than that would be dangerous and you don't want to hurt people, right? So we'll stack them, so high, and then we can move a stack of container ships. And then once they're done, then we can take that stack and we can start working the stack again. So take the item that's on the top of the stack. So what was the 5th thing on the container ship, if we take them off one at a time and put them on the stack, is now the top of the next stack that we're working. It's just a fun way to visualize things. One of the labs we'll work on next week, we'll kind of imagine we have a stack of French fries. Because when you're done, French fries. So when you're done cooking French fries, you just throw them in the French fry bin, which is like a stack of French fries, right? The fresher ones are on top. The older French fries are on the bottom there. If you're lucky, you get the fresh French fries. If you're unlucky, they've already scooped off all the fresh ones, and you get the ones that have been sitting in the warmer for an hour, and they're just gross by that point. It's a little bit unfortunate. So we can use stacks to model things that look like stacks in the real world. That's all. And then in terms of stacks, let me go back to my other solution here.
How do you code the stack?
That's what we're going to do, actually, right now. So we're going to make our own class for stack. So stack has an init. So you can make a stack here. It has self.data, or items, or whatever you want to call it here. I like data here, is a list. And we're going to use a list because it's easy for us internally here. And then we're going to add a method for push that takes an item. We're going to take our self.data, and we're going to append the item. We're going to define peak.
What is push? Push is just put it there?
Push adds the item onto the stack. Yep. We're going to add peak. That just returns the self.data. Now I want the thing on top, and if I'm appending, that'll be the thing at the end here. Right? So it's the length of self.data minus 1. Right? And then pop here, right, gives you back that item. Return self.data.pop. There's actually a pop function in the list. Right? This removes and returns the item at the index. The default is the last.
So, sir, earlier, why did we do -1?
So remember the length of data, if I have one thing, I don't have it at index 1, it's at index 0. If I have 10 things, the last one is at index 9.
Yeah.
Right.
Why don't
So
you just put -1? It goes to the last one, right?
yeah, there we go. I don't even have to do the length. I forget sometimes Python's super helpful. Yeah, thank you. That's a good shortcut. Right? Cool. So we now have a stack here. So we have wrapped a stack around a list here. And if we think about performance of these things, right, that big O notation, right? How long is the average? And again, best time is, we don't really care about best time because it's very rarely ever best. But average time is very important, right? How often will this usually take? And then worst case is important to know too, because sometimes we could get the worst case here. So if the worst is really bad, it might not be a good solution here. But on average, right, how long does it take to add something to a Python list? Right? In terms of n items, how long does it take? Our amortized average here. It's O of 1, it's constant. Right? No matter how many items we have here, on average, it's one operation, or a constant number of operations, because the Python list, remember, it resizes itself every so often. But the way that it works with the geometric resizing is essentially that one time that it has to do that is averaged out over the next bunch to still make it constant. Right? I drew that fun picture where, like, if you lay all those bars down, it's just flat. Does that ring any bells? So on average, it's constant. Worst case, right? So this is my average. Worst is going to be O of n. So I have to move n items into the new list for storage to make space for this one. But most of the time we don't get this because we know the average is constant here. We know we're going to be okay. So every so often it'll be a little slow. We'll get little blips here and there and there. That's what the graphing exercise was. Right? You'll see the little blips every now and then, but most of the time it's really fast. Right? For peak here, to look at the last item, my average time is O of...
Why does it really matter? I'm asking out of my ignorance, like, why is it really important to know at the time it takes?
For the things we do in this class, it's not important. But when you start doing something millions of times, like at scale in an organization or in an application that you use millions of times, those tiny bits of performance increase really add up. So every little bit of performance you can squeak out of an application where you're doing something bunches and bunches and bunches of times matters. So unless you're Bitcoin, where your entire goal is to waste time and electricity and energy, then you don't care about performance, right? The goal was to make this slow on purpose. We don't want to do that, right? We want to optimize eventually. For our purposes, we don't really care about optimizing because it's never going to hurt us. You know, we're never going to do that many zillions of operations. But there are problems that we solve, and in data science, when we work with large sets of data, if we're working with billions of points of data, and you can speed something up 3 times faster every time you compare one of those pieces of data, 3 billion speedups is a lot. So looking at why things work and how fast they are when we hold data in memory is an important piece of this computer science idea. When we do data science, we use those same principles as we're analyzing data. Yeah, it's really boring for now because it's never going to matter for us. But if we do it zillions of times, we would see the speed up. That's all. Yeah, so average is 1, and then our worst case here is still O of 1. Right? No matter how many n items I have, I can always get to the last item like that because Python knows where it is. Right? It's always accessible with a -1. Super fast. To pop something off here, remove on average is going to be constant. Right? I can remove the last thing like that, perfectly fine. The worst case, eventually it is going to resize itself and it will shrink if I've popped enough items back off and it's like, hey, I have room for 500 things and you only have 100. I probably don't need to keep that much memory. I can give some back to the operating system, so I will resize lower and give some back. But Python manages all that for us, but we just want to be aware of the timings here. So it trades off giving the memory back for a little bit of performance hit. So anytime we deal with stuff that has to do with performance, we're dealing with space constraint, which is our memory constraint, and time constraint, our processing power constraint. Right? And there's usually a trade between the two. If you can take up more space, usually it's faster. Or if you can do it slower, you might be able to use less space. Right? So by doing more processing, you might not have to store as much information. So there's always some trade-offs there. Depends what our goals are and what we're trying to achieve and what sort of resources we have available. We're super spoiled nowadays with laptops carrying around ridiculous amounts of power. Like the calculators you folks have in math class have more power than computers did back then in your calculator. It's crazy. But we were still able to get to the moon in 1969. That was kind of cool, right? But we still can't keep like a room at a decent temperature. HVAC is the harder problem to solve than getting to the moon somehow. I don't know. I feel like it shouldn't be hard to get warm air and cold air to places. That's what I get for not working in that industry. All right, so pop, push, and peek. Ways we work with our data in a stack. And we just throw stuff in here. Whatever that data happens to be, perfectly fine. We'll just take it. So that's a stack. That's the easy one. Okay. The other kind of data structure that we're pretty familiar with, but it's a pretty basic one here, is a queue. Yeah.
But how do you actually command the stacks?
So you would use a stack. So like in my code, if I wanted a stack, so stack of fries is a stack. I take my stack of fries and I push, here's some fries, right? And I could push more fries, and probably not strings, right? You put other things here, more fries, and at some point now the fries are going to be old and gross at the bottom. Depending on how fast you eat your fries. Or if you order McDonald's fries, they're always gross, no matter what, because they're McDonald's fries and they're nasty.
So if you want to pop, you will end up only with some fry.
Yeah, I would get more fries because that's what I put on last. Right, the last thing on is the first thing off. So other things we might do then to make this a little easier to use, we might have an isEmpty. Return length of self.data is 0. It's probably the easy way. Right? If we have nothing left, we're empty. So then you can do some sort of loop, like push a bunch of fries on, and then you can say, while stack of fries is empty, and we want like not is empty, right? We can print stack of fries dot pop. More fries, more fries. Punch a bunch of fries on, whatever, and then pop them all off until we're empty. This is what they should do, right? They should empty out the fries before they put the new ones in. So they don't get those old gross fries in there. But life's just easier if you don't eat nasty French fries. Who has the best fries around? Do you like curly fries? Curly fries are definitely the superior fry, right?
I agree.
Definitely. Oh yeah, curly fries are so much better. Was it Checkers has really good curly fries? Arby's are okay, but Checkers are better. No other French fry enthusiasts? Wendy's are okay.
McDonald's.
Really?
Those are our favorites.
They put meat flavoring and milk in them.
Yeah, when I think of it, it's the best.
You're welcome to like them. I apologize. You enjoy the fries you like.
It's probably because you have them, you're like so exhausted, just like, oh, McDonald's, like an oasis. That's what I have, and then McDonald's is the best for sure.
Really?
Yeah, I mean, like I only have it while traveling.
Okay.
I'm super famished, so.
But for burgers, Burger King.
Burger King had the best burgers for sure. They're like flame grilling before they freeze them. Really does add a lot of flavor. I do like Wendy's that they cook them fresh, but I'm a vegetarian now, so I don't eat any of the burgers anyway. But the quarter pounder with cheese at McDonald's is supposed to be cooked fresh, never frozen. So it's supposed to be better, and then hopefully you don't get one that's been sitting in the warmer for an hour and in violation of health code sort of nonsense. But we'll just pretend that everyone follows the health code at all the McDonald's, because everyone who gets paid so much an hour really cares about that sort of stuff, right? I'm sure. Yeah, it's,
Have you had any friends that used to work there?
yeah.
Like, I'm sure they told you like a bunch of horror stories. So.
Yeah, that's why I liked that it was supposed to be cooked fresh. Like they don't keep any ready to go. They when you order them, they'll make it fresh for you. But that's okay. We're all just better off not eating fast food anyway, because it's terrible for our health and garbage. But it's fast and it's cheap, which is so weird. The good for you foods like fresh fruits and vegetables are more expensive than the cheap crap. It's crazy, kind of crazy, but that's okay. What?
Unfortunately.
All right, so our queue class. Now you're familiar with queues. Now, if you're British, you know a queue is a line, right? You get in the queue at the grocery store, you get in the queue here, you get in the queue at the bank, these sort of places. You get in line. So with a line, the first one in is the first one out. There's no cuts, because you'd be pretty pissed off if someone gets in line ahead of you, right? So we'll have our init method here. Again, we'll set up self.data. Self.data is a list. And then you have an enqueue that takes some item. And we're going to add it to the data. Append the item. And then you have a dequeue. Dequeue? QU? E? So what are the silent letters in the word queue? Is it UE, UE? They're both silent? All four of them?
Yeah.
It's just the letter Q? Or is it, they also have a Q, QUE, and you have the Q, UE. I don't know why. This is crazy, right? Oh no, that's a different Q. That's the CUE. That's also a Q. I hate English. English is way too hard. So you can NQ, you can DQ. So to DQ something, right, we're going to return the front item. Now the front item is going to be...
In Q, you put in the first place, right?
Well, in Q, you add it to the end of the line. So a pen will put it at the end of the line, right? Yep, so to DQ, we want to return the self.pop, self.data.pop 0. Grab the front item here and give it back. And then you also have a front, just a look at the front like a peek was. We're going to return self.data at 0. Right, and probably the same is empty is nice. Like this just works out nice. Now, if we wanted to do some sort of obnoxious inheritance, we could. I'm not going to. The book loves obnoxious inheritance, which is nice, and that's a good object-oriented principle. It just makes these things harder to look at, so I won't bother with those. So, on average, right, how long does it take to add something to a list? We already said this one. This one is 1. O of 1. So almost all the time it'll be super fast. Again, we know the worst case is can be slow, but that's on average it won't be slow, and we'll be okay with that. Now, DQ, how long does it take to take the first item out on average?
1.
There's 1?
Yeah.
N. Right? So the more items I have, the more things have to shift back to fill that gap. I took the first thing out, and I left a gap. Lists don't like gaps, right? So everything shifts down the line. Everyone moves up a space. So n people have to do something to move up a space in the line. You get dirty looks if you leave space in the line, which is silly because you're all still going to get there at the exact same time, whether or not there's space in the line or not, right? Compressing that space doesn't actually get people anywhere faster, but we like the feeling of movement when we're in lines for some reason. People are just weird like that, right? So on average, it's n. The best case is still n, right? The worst case, it's still n, right? It'd be 2n, right, if we had to resize at some point, but 2n is still n, thanks to the magic of math, right? We get to throw away coefficients. The front here, average is constant, right? We can do this in 1. We know where the front of the line is. Here's the front of the line, right? So this performs badly here, right? Having to, take out the first item every single time and get n performance, if I'm adding people to the line, taking people out of the line, adding people to the line, taking people out of the line, this is no good. If you run an amusement park and your line runs this slow, you're going to have trouble. Right? You make money by getting people through the lines, right? So they can buy more money, spend more money at concessions. That's where you make money at the amusement parks. Yeah.
How do you choose whether to use a queue or a stack?
So it depends on the problem, right? What problem we're trying to solve. So like those pre-done burger shoots, when they're like, hey, I've got 5 burgers ready to go, because I can just hand them off here, right? When you add a burger to the queue, you just throw it down and it goes down that little chute at McDonald's. It's the front of the queue. When they go to serve your meal, they're like, okay, here's your 3 burgers. They just pick up the first 3 burgers off the front. Yeah, first in, first out, or last in, last out. Yep.
All right. So
Yeah.
what about the stack? How should we use it?
When the thing we're modeling fits a stack. So if we're stacking things up like containers, we're going to stack a bunch of containers up. You only ever touch the top one. If you touch the bottom container, you have an OSHA violation, right? You're going to hurt somebody. This is first in, first out, or last in, last out. Right? Whoa, clicked the wrong thing. Stack is last in, first out, or first in, last out. Right? Both ways. So some people like to turn these into words. Like this is LIFO, L-I-F-O. I don't know. People like all sorts of weird things. Or FILO, first in, last out. Or LILO, or FIFO, FIFO. I don't know. FIFO, FIFUM. So all sorts of weird things. But this is slow, right? This is not a great use here. So can we make a better queue? Class, how about a faster queue? Can we do faster? I'm glad you asked. Yes, we can do faster. And you guys are onto this. So the other ones are fine here, right? We don't need to worry about any of that. I'll just copy paste. But DQ is the problem, right? The problem with DQ is we have to move things. So what if instead we had a self dot front starts off at 0 here, and every time I DQ something, we're going to take my item is self.data, and we're not going to pop it here, we're just going to go to the front. Self.front. And then I'm going to take self.front, I'm going to add 1 to it, and I'm going to return the item. So grab the item here, and then I can go and set this to null if I want, right? This is the better thing to do, clear out your references so that Python's not going to hang on to it. You say, hey, whatever was there, it's none now, because I don't need my list storing a reference to it, because if someone has a reference to that piece of information, it can't get cleaned up by the garbage collector. I'm going to give it to you, and if you are done with it, then we should let it get garbage collected. I don't need to hold on to it in my list. That's all. So it saves a little bit of work here. We can return the item, and then now front is not here, front is self-front. Yeah.
I didn't get it. So we're saying that item would be the first item in self.data, right?
Whatever the front value is. So front will start at 0, and then every time I take an item off, we'll increase it by 1.
Oh, okay, so I don't pop the first one.
We're not going to take anything out of the list. We're going to leave it there, but leave it empty. So my list will keep growing as I add. So if I add 10 things and take 10 off, my list is still size 10. I just have 10 nones. If I add 10 more things, my list is size 20. I only really have 10 things in there, but I got 10 nones and then 10 things. Yeah?
That's just what I was going to ask.
Yeah.
Yep, so this will just keep growing. So we're trading off space. We're keeping more memory here to increase our performance. So what's the average performance now if I never pop anything?
1.
Oh, 1, that's right. But we've traded increased space.
But why doesn't it increase performance if it increases the memory usage?
So memory is relatively cheap for computers, right? I've got like 16 gig of memory in my computer, right? Storing 1,000 things barely scratches the surface here. So if I'm only going to have 1,000 things in my stack or my queue here, I don't care that it uses up 1,000 extra 8 bytes at a time, right? For memory references in a 64-bit system. So 1,000 times 8, I've used up like 8 kilobytes extra of memory out of my 16 gig. So I don't care.
So it's better to use more memory than resize the list every time?
Depends. It really depends on what we're doing. So if I'm doing trillions of things, my computer doesn't have room for trillions of things.
So
It'll run out of space. I can't do that. But if I can make that trade-off, sometimes it's worth spending a little extra memory usage and saying, hey, Python will hang on to more memory to make things compute faster.
Can you mix both of them?
Yeah. Yeah, there's ways to do that, and some of the data structures we look at are better than others at that sort of thing, and that's why we spend so much time looking at all these data structures to find out what's fast at what, so that when we're solving problems, we find the right tool that fits the job to solve it quickly and efficiently.
So like you keep substituting the item by none once it gets removed from the list, but once you reach some kind of limit or memory, you just resize it and then start doing it again.
We could,
Does it
yeah.
work?
Yeah, so we could change the resizing bit here so that we don't need to shift every time. We could do our own sort of like dynamic, hey, if we're 2 times as many nones as we have actual items, now we should go resize. Or we could do that sort of logic like we did with the array-based lists that resize themselves. We could do that exact same thing here, right? But we don't want it to happen every time, right? So we can delay it to have a little bit of memory trade-off, but don't get too large, right? Don't let it balloon out of control. Let it get 2 or 3 times bigger than it needs to be before we resize it, and then take that performance hit, because that would average out then to constant again, right? So we can get better here without using unlimited space, for sure. But it turns out we can do better than this, right? Without all that extra work, right? So we can make a class for a circular queue. This one's my favorite, circular queue. We just do the letter Q because it's fun like that.
Is that another kind of data structure?
I'm sorry?
Is that another kind of data structure?
So the queue is the kind of data structure. The way that we implement it is with a circular list, or just a static list, or just a list. So these are ways of implementing a data structure that impact its performance. But the data structure itself is just NQ, DQ, and front. Right? It's the method. So that abstract idea of here's a queue, you figure out how you want to implement it based on how you want it to perform. Yep. So the circular queue is really fun. It has a front and a back here. And then I think that's fine for now. So we enqueue. Okay, let me just copy these here. We can enqueue, we can dequeue, we can do is empty. So we enqueue something. Those all tabbed in wrong. That's weird. There we go. We're not just going to append it, right? Because we need to put it at the back. This one gets a little funny here as we go. But essentially what we want to do is we're going to take this times, we can start like an initial size. Initial size is 10. So we want none times 10. I think that works here. That should give me a list of 10 nones, where I have the front and I have the back. And when I put something into a queue, I want to add it to the back. So I'm not going to append the item. I'm going to say, hey, data at the self.back. We're going to assign that the item. Because I'm going to pre-size, hey, I've got 10 spaces here in my list. I'm going to put it at the back.
So, sir, is it like you changed it from append to self.back? Because if you kept it as append, it wouldn't work.
So append would add to have 10 nones, and now I have an 11th item. So I don't want the 10 nones in front. I want to use this space that I have allocated to be more efficient with my memory use. Yep. So I'll set that to the item, and then self.back goes up by 1. Right, when I add something, now the back index changes. It was 0 when I had no items. Every time I add something, back will move. But then, eventually, back is going to fall off, right? If I have 10 spaces and I add 10 items, back will be 11. There is no index 11. This is no good here, right? So what we want to do here is, because this is going to be a circle, right? We're going to take up space as we go. So let's let me draw a picture of it here. That might be easy. So if we imagine this list here, right, with 10 slots for something, or however many slots this is, right? This is fine. It doesn't need to be 10. So when we add something, it adds to the back. So we have front is 0. We have back is 0. Right? We add the number. Let's add number 1. Now back goes to 1. We add the number 2. Back goes to 2. Right? We add the number 3. Back goes to 3. Right? If I take something off now, I'm going to take off the 1. So we take off the 1. Front will now be 1. Let's add number 4. Back is now 4. Right? We take off that one. Front is now 2. That one got taken out. What we want to do here is circle around. So as I keep adding items, 5, 6, 7, 8, I want to come back to where I have open slots. And I'll put 9 in here. Right? Now front is still 2, but the back now is 1. Index 1. The next place to go is here. We want to reuse the space as stuff gets taken out. So if I put 10 in and take 10 out, and put 10 in and take 10 out, I never need more than 10 spaces. Right? I only need to increase my size if I don't have room for it in my circular storage. So what I can do, right, is I keep adding things. 3, I take out 3, I could add 10. Yeah, I could add 11, take these ones out, I could add 12 and 13, right? And I've never used more than 10 memory addresses, or 8. I'm sorry?
What if you have 10 numbers?
Yeah, so now we would, like, once the back meets the front, I have a problem and I need to resize. Now we need more spaces here. So that's the next piece we're going to look at. So we enqueue, we move back, and then we want to change back. So we're going to say, hey, if self.back is greater than or equal to the length of self.data, right? Look at how many storage spaces I actually have. Now, it's probably never going to be greater than, but this is probably safer just in case I screw something up rather than just checking if it equals. I need to resize. So we'll call self.resize, and then I'm going to say length of self.data times 2. We'll double. We want to do this geometric doubling here. So we haven't written it yet. We'll get there. So this resize comes from when we did the array-based lists, where we have to make a bigger array of storage, move everything down. We have to do it a little bit differently here. We'll look at that in a second. So we add an item, we add it to the back spot, then we move back, right? Then we see if we need to resize or not. Then we also, or we could check here, this is not actually going to work very well, is it? Because if back has gone around back to the front, and I'm at like 2 or 3, it'll never be bigger than 10. But when I start assigning, right, if I said, hey, back is now 6 here, I would overwrite the first item here. Back never changed here. So I don't actually want, if it's greater than or equal to the length of the data, I want if back is equal to self.front. If the back equals the front, now they're touching and I'm in a bad shape here. Right? When I've added something and they equal each other, then I'm out of room, right? So if we look at, I've added all these items, right? So if we go back, undo a bunch of these. Come on, Word. It does not like my undo. Scroll down, there it goes. Keeps wanting to do that. Right, so as we add 4, 5, 6, 7, 8, 9, 10, now back is going to be 2, right? And front is 2, I'm out of space. But up until that point, when back was 1, I had room for the 10. Right? So when it equals, then I need to resize here. So it's not based off the length here, it's been when they match. I have to resize here. So we can write resize, we can define resize, self, and then we want a new size. So we're going to make a self data, but we don't want to change self data yet. We want this to be new data is none times the new size. Right? Make a list of this many blanks based on the new size.
Yeah, that's specifically resize if when the queue is growing, right?
Yeah.
What if it's shrinking?
So we could resize to smaller if we wanted. We just haven't yet. So we could give it a smaller new size, and that should still work. Right? So we'll make sure we can handle both cases here. So to move data into the new data, right? I want to go for index in range, and I want to start at self.front. Right? I want to go to the front, and I want to go to either the end or the length of the queue. Right? So this is like, this gets a little funny here. So maybe we want to actually calculate that. So to know how many items we have, we'll have, items in data. So I can't take the length of it here, but if I take the back minus the front, if back is 7 and the front is 2, I should have 5 items in there. But if I've gone circular, I have a problem. So I've got 2 ways to look at it, right? I can say, here, this is if my self.back is greater than self.front, my items in data is going to be self.back minus self.front, right? If I haven't circled back around yet, I can do this arithmetic. Otherwise, right, my items in data is going to equal items in data, right? It's going to be, so my back is less than the front here. I'm going to have from the front to the end, so it'll be the length of self.data minus self.front. So if I have room for 10 things and my front is currently at 5, right? That means I have indexes 5, 6, 7, 8, and 9 open. 5, 6, 7, 8, and 9 open. So 10 minus 5 will be 5 items up until it hits the end, right? And then plus my self.back. If back is at 0, I add no more items. If back is at 3, I have 3 things, right? Index is 0, 1, and 2. Yeah.
Could you just take the absolute value of back minus front, or front minus back, like either way?
There's probably some tricky math we could do, but I don't think you want absolute value, right? Because if you're saying, so if back is 3 and front is 5, I have 8 items.
Oh. Yeah.
Right? So I think I could, if it's less than, I could add it.
Yeah, never mind.
Somewhere, yeah, somewhere in there, I'm sure we could do some fancy math. But I think this is a little bit more straightforward for now for the arithmetic we're doing, right? So either have not circled around, and we can do a quick back index minus the front index. Done. But if we have circled around, we go from the front to the end, and then from the beginning to the back, right? Because we've gone in that full circle. Then I can go for item index range from self front oh man, to the end, I guess, to length of self.data, right? Now, I have the index of where the item is currently in self.data, right? So my new data at the, what? At the value, right? I've got a couple ways I could do my loops here. So this will be starting at 0, right? But I want 0, so I need some way to store, like this is my new data, index is 0. It's my new data index. Right, we could do that, sure. And then it will equal self.data at the index. So this will take from the front up into the end here, right? But then we need to circle around and get the rest of them. So after we've done that, then we can do for index in range. I'm going to go from 0 to self.back. That's only though if we're less than, right? Otherwise I've already copied that. This is messy, sorry, let's see. So from the front, this is from the front to the end, because we can copy nuns. It won't hurt anything to copy nuns. It's probably not super efficient, but that's okay. Or we can look, so we can say, hey, if self.front is, let's see, if this is less than self.back, then we do this. We just copy from there up until self.back. And then we can take the new data index +1 as we go. So if the front is before the back, right, we haven't circled around, just go from the front to the back. Now, but back is a valid index. No, this is the next location, right? So this should work because we want to stop before then. So if back is 1 and front is 0, there's only one thing at index 0. We'll copy one thing out. So if it's not less than, right, my else case then, index and range from, I want to go from self.front to the length of self.data. So copy all those values out, right? Then we need to go for index in range from 0 to self.back. Copy all those ones out. Right? So if we haven't circled around, go from front to back. If we have circled around, go from front to the end, and then go from the front to the back. Or from 0, right, the start of our internal storage to where the back actually is. So this should catch all the ways that this could loop around here when we resize. Then when we're finally done, I can reassign data. So my self.data equals the new data, and self.front is going to be 0, right? And then self.back is going to be the items in data, right? However many items I had. That'll be the back index, because I just resized here, right? So this was how many items I had, yeah.
If you're resizing, why don't we just add one like empty space and use it for a loop to just send the other elements forward?
Because that's going to be slow, right? We will have to do this geometric thing where we double our size. Otherwise, every time we resize, it's going to be n operations. And every time I want to add one space, I'm going to have to do that whole thing again. So we're increasing our size to double what we need it to make sure that it only happens every so often, so the average performance will be constant.
We're doubling.
Yeah. Yeah, so we're going to double our size every time to make sure that I don't have to resize again until I've gone n number of operations again, to make sure that it will average out to constant time. That's why we do these geometric doubles. So all this work to move to a bigger internal storage array, reset our front and back, reset data, and we're good to go. So at some point in here, we probably should none them out. I don't think it really matters that much. I think the book does, but it'll be okay. So resize, if we're going to a smaller size, should still work, right? So if we had room for 100 things, and we're only actually storing like 30 things, I should be able to make size 50 and store 30 things in that size 50 from wherever the front is to wherever the back is, right? Either whether or not we circle around or not, it should be able to resize to a smaller size if we want. So when we NQ, if the back touches the front, right, we've circled all the way around, resize. Okay? When we DQ, okay, so our average performance here is going to be constant now, right? Our worst case, we'll have to resize, we'll do N operations, but that's only every so often, right? Because we'll be able to average that out, thankfully, thanks to the magic of math, to be worst case of N, but on average constant. To DQ something now, we'll take the front, we set the front to none, change front. But now front could also circle around the back. Right, we want to make sure that we're going to make, so if self.front is greater than or equal to, oh man, hang on. Oh shoot, no, we messed, so we still need to do that moving here. So hang on, so if self.back is equal to the length of self.data, self.back equals 0. Right? If we reached the length here, circle around. We have to do the same with front. Right? If my front becomes the length here, put front back around again. Right? This finishes the circle. So it keeps our internal storage. And we can keep DQing things all we want here. Now, bad things could happen if we keep DQing when the front reaches the back. Right, because that means we're empty. So our isEmpty is not the length of our data 0, right? The isEmpty is self.front equals self.back, right? If the front reaches the back, I have no items left, right? I've added 1, 2, and 3, and I took out 1, 2, and 3. What I've called front now is now the back position. They've matched, I'm empty. So if we're empty, we can say, hey, if self.isEmpty, raise a, I don't know, some error, what kind of, I think we've got an error in here somewhere. There's a good one in here. What do we get? There's an error we get when we try and get an empty list, right? What is it here? Idle. Let's do it here real quick. List equals a list, some list.pop. Index error, there we go, index error. So we should raise an index error. Raise an index error. Q is empty, right? This is probably the right thing to do, right? You can't DQ something for an empty queue. So if we're empty, we're empty. But now, when we DQ, right, on average, it's O of 1. The worst case, still O of 1, right? We haven't done any resizing downwards. If we want to resize downward, we could. We could check to see, hey, are we actually storing n number of items? Is that, less than some factor of the size we actually have? We could resize smaller. For now, let's just not bother, right? We could add that in, to do resize smaller. Smaller. There we go. I like how it colors the to-dos, so they jump out at you. That's helpful. It's a common thing to add in your code.
Same thing as fixing, right?
Yeah. I think it colors fix me's too. Yep, fix me. So to do is like new features, fix me is like it's broken. It doesn't, whatever. It's just a silly semantic. Like calling this the pound sign versus the hashtag. It's okay, it's just semantics. All right, so now we have a circular queue that is pretty good performance now, right? We've solved all the performance issues and we're not going to have unlimited memory, assuming we fix the resize down, right? That sort of thing. And it's going to be more efficient, right? We could get pretty similar with the faster queue if we did the resizing, but it's going to have to resize more often, right? As it gets bigger and bigger and bigger because it doesn't reuse that circular space. So in terms of like O performances, it performs the same, but we know ours is technically faster when we're circular, or we're more memory efficient. So we haven't gained any performance speed really from this one here, but we're more memory efficient now. So maybe I shouldn't call this, this is the better memory usage and a faster queue. Yeah.
So is a circular queue widely used in the industry?
So if you're using a queue, it's probably built on a circular queue. That is the most efficient way we can build queues with this circular memory usage thing here. Yeah. So turns out there's actually a queue class you can use. We don't have to write our own here. You can go import queue.
How about stack?
Or no, is it?
It depends on the application.
Yeah, and there's built-in Python queue class. What is it here? What's it called? Queue, synchronized queue. Yeah, queue. There it is. Queue. It is a queue. Queue class. Isn't it? Queue? Q.Q. An annotation. So it's you're adding information about the code to make Python do some cool magic stuff. We haven't done a whole lot with annotations.
We're going to learn it.
We don't really get into them. No, you'll find them later. They're not super hard they give like additional features you can do with them. Queue. There we go. Import queue. So if you want to import queue and like not do any of this, you can do that. So we can look at the Python queue code. Where is it here? Yeah, it's the libqpy. Okay, so we can go find our Python install. So find C program files. Oops. How's it? 6? No. Users, app data, local, Python. No? My goodness, where? I hate this. Sorry. Where is my Python installed? That's where app data local programs. There we go. Local programs, Python 312, lib, q. Let's open it in PyCharm. So here's the Python library Q code. We could just go steal theirs, right? Is it going to open for me? There it goes. Class Q. Init for a max size. Init's the max size. Private init for a max size. Where's our private? Here's the init. Self Q equals a dec. Okay. You go back one of those. Where is that defined? My goodness. This code gets fun, right? Let's see, where did it go? So I think we're importing it. So it imports the dec collection to use its own queue. All right, well, we've got to go find that. So collections.dec. Collections. ABC? No? Oh my goodness, what is even in here? Where's the dec class? Python dec class. Where did it go? Collections, dec. Huh. A double-ended queue, pronounced dec. See, Python told it it's true. Where does it give us the code for it? I wanted the code. Huh. I thought we had it in here. I'm sorry. Is it not? It's not in collections there? I'm not sure where it went, but that's okay. We can keep looking at queue. But looks like dec is going to do most of that for us. And this one does threading, which is super fun for us. So it's thread safe. That gets crazy. We don't even get into this one here. Queue size, it can get the size, if it's empty or not, if it's full or not. We can put an item here. If we're not full, then you can put the item. So that's our put here. Where's put? Yeah, it just goes and appends to the queue. Sure. So manage all that in the, it's got to be in the dec here. Where's the dec class? Go to implementation. Here it is. Oh, this collections. Okay. Here's our collections here for this one. Here's the deck object. So you can. Is it not doing any of these? Oh my goodness. Which deck is it actually then? That's obnoxious. Is it not done? Where's the collections code? Collections module. Yeah, where? All right, I can find the code for you later. I don't know where it is right now, and that's frustrating. But this is not super interesting. But we can find out what it uses eventually. We'll go find its code wherever it happens to be. Yeah. That sound good for today? We did stacks, which are just fast out of the box because lists are great. And then queues, we have to do a lot of work to make them fast. Right? Super fun. All of this to say you can just use the ones in the library. But the reason why we build them is we understand what they're fast at and what they're slow at, and why they're fast and why they're slow. Right? That's sort of why we go through these things. Right? All right. I will see you.
I'm sorry.
No, go ahead.
Are you gonna use them for the project?
Yeah, we'll have a project using stacks and queues. Yep. We can use the built-in ones, but we just want to use them to understand how we interact with them as well. Yep.
Are there built-in ones?
Yeah. Yep. Yeah, just like that built-in queue, you just import queue.
Yeah, so that one?
Yeah.
That's a queue, right?
So it's a double-ended queue, so you can do front and back additions. And we'll talk about that on Thursday.
Right.
Yep.